So bits and bytes. So a bit is 0 or 1. It's the language of computers and digital cameras, so to speak. And a byte is just 8 bits. And this allows us to have 1 byte represent so many different discrete values. So if we have 8 bits, how many different values can we represent with it? So more than 16. And the reason is that just like we have when we are talking about our own counting system, where versus binary, which goes from 0, 1, and then, let's see, let's do this, and then 1, 0, where we count from 0 through 9 before we go to the next place. So if we have, let's see, I'm trying to figure out how I can make this, explain this more easily. But let's say we have the number 128. Now we know what this is intuitively because we've learned how to count in base 10. But if we go back, and I'm not doing this to try to say that you all are stupid, because I know you're not, but I'm just trying to break this down for you. We have, and this is going to sound very elementary, but we have 3 places. We have the hundreds place, right? We have 100, and then we have a tens place. We have 2 of the tens place, and then we have a ones place. Now, when we have 3 places here, we can represent how many different numbers when we're thinking about the decimal system. So if we have the ones place, the tens place, and the hundreds place, how many different numbers can we represent? We have 0, 0, 0, that's 1, 0, 0, 1, that's 2. 999, well technically 1,000 if we include 0, right? Okay, now keep this in mind when we're talking about binary. Now binary looks like this, but it has the concept of places as well, but it's just a little bit different. So we have a ones place, oh boy, this is going to get confusing, a twos place, a fours place, an eights place, a 16s place. And what ends up happening is that when you figure out that what you did up here was basically you did, okay, well the ones place can have 10 different digits, the tens place can have 10 different digits, and the hundreds place can have 10 different digits. You figured out that, okay, when I have 3 digits, I can have 1,000 different values. In binary, when I have 8 different digits, it's 2 times 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 2. That's 8, so that's 2 to the 8th power, which is 256 unique numbers that can be counted with 1 byte. And you can, if you want to convince yourself of this, you can go home tonight and you can start from 0 and count in binary. 0, 1, all right, 1, 0, okay, 1, 1, and then 1, 0, 0, and then 1, 0, and keep going and going and going. You will figure out that you have 256 different values. Okay, now, it's possible to convert numbers from binary to decimal, but I will spare you of that horribleness. Okay, now, when we are talking about bytes, remember that we said that there's different file types that exist, and one of the predominant file types is JPEG, and that has so many bytes attributed to it. So does anybody remember anything about the JPEG file type? It was how many bits could we store? We said it was an 8-bit file type. So that means that each color could have 8 bits of information. So we could have 256 different values for red, 256 different values for green, and for blue. Now, the same sort of thing happens with histograms. The histograms are computed based on a level of black to white, where black represents the value 0, and white represents the value 1. Now, what's important to realize is that these histograms that we've been looking at don't talk about color. It's just talking about black and white. But there's an inherent problem with converting black and white to color. And in fact, there's a couple of different ways that we could, well, no, I said it backwards. There's an inherent problem in calculating, did I say it right? Calculating black and white from color is what I meant. I don't know if that's what I said. Okay, but anyway, so we have 256 different values that we can deal with, and we have to try to convert this color down into it. And so, as you recall, we have the JPEG file type, where each color can represent 8 bits of information, so 256 different values of information. And so to make that a little bit more concrete, if the red section is 0, then there's a complete absence of that color. If the green section is 0, there's a complete absence of that color. If the blue section is 0, there's a complete absence of that color. You add those 3 up, and it's just black. There's just no color at that region. But if we do the opposite, 255 plus 255 plus 255, this represents white. And so we can even get all of the colors in between. So if we had the complete presence of red, so 255 for red, 0 for green, and 0 for blue, what color would we get in the end? Yeah, just red. So we could do the same if we had 0, 255, 0, we would have just green, so on and so forth. And we can combine these. So if we do 255, 0, 255, we would expect a bright purple, sort of it's a bright purple rather than a violet, and so on and so forth. Then we get this entire gradation, all of these changes in colors that exist because of this. So we could add blue and green. So if we had 0, 255, and 255, what do you think the color we would get is? That was grammatically terrible, but what color do you think we would get out of that? Yes, cyan. Perfect. All right, so blue plus red is sort of like a violet, and a red plus a green. So 255, 255, and 0 is a yellow. And so once you start to understand this, hopefully a lot of these other aspects of computers will start to make sense. So you might have seen something like this. So this is Photoshop's color picker, where you can pick a color among all of the ones that are available to you. And so just to give you an idea, if we have 256 values for red, 256 values for green, and 256 values for blue, how many different colors could we get out of that? So yeah, it's a lot. So it's 24 bits of information, and that is going to be something like, what is it, 16 million, I think, or something like that. It's a lot. It's a lot of colors. So rest assured, I don't even know. I can do 2 to the 24th in my head. I'm not that good. So there's a lot of colors here. Now, what we could do is use this color picker to try to figure out different colors. So what we were talking about before was doing, let's say, 255 of red, 0 green, and 0 of blue. Keep in mind that there's a lot of other ways we can compute colors, but we're dealing with this RGB section here. And you see that the end result color at the very top is this red. And so we could do the same. Now, and I'm just using these extreme examples just to show you, very concretely how we can mix some of these colors. But usually what we see are variations, or all of the intermediate values that exist between them. So here I've combined about halfway, about half a red and half a blue, so we get this sort of deep violet color that exists out of it, versus a complete, oops, no, I think it gave me an error, yeah. Okay, here we go. Rather than doing something like this, which is a much brighter purple. Okay, but going back to this. All right, so we have all of these colors, but as you've seen, histograms typically don't show you this color information. It's this black and white information that we were talking about. Did you have a question?
Yeah, I was just wondering, so then you shoot digitally in black and white,
Mm-hmm.
you're losing a lot of information.
Yeah, that's right. Yeah, when you shoot digitally in black and white, you are throwing away all of the color information that exists. So you're basically going from having three bytes of information per pixel, because you have 1 byte for red, 1 byte for green, 1 byte for blue, and you're just replicating all of that information at every pixel. So if you make all of these numbers the same, so for example, 128, 128, 128, you just get this sort of boring gray color. And as you increase all of them or decrease all of them at the same time, it's just the various levels of gray that exist. So when your camera is taking a black and white photo versus you taking a color photo and then later converting it to black and white, you are just throwing away 2 other pieces of information. You're just basically making it just this luminance, or just this this amount of brightness that exists within the scene. So very much like digital zoom, I don't recommend you take photos in black and white on your camera. Just do it later if you want to do it. You have more options at the later time, because as we'll talk about in the color lecture, it's more complicated than just converting a photo to black and white. There's many options available to you, especially when you have that color information available to you. And as a teaser to that, and one of the things that's important to us, is this discussion about how a histogram converts color, this color information, red, green, and blue, to this grayscale, to this black to white range that we were talking about. So how do we do this? How do we convert this change of color to this grayscale? To do that, well, okay, actually let me ask you, so what would a reasonable person do in this case? If we had 3 pieces of color information, we needed to just make 1 piece of color information, how would we do that? We could just average the red, the green, and the blue, for example. And then we would get something that looks like this, just this sort of dull gray color. Okay, but in order to figure out how we actually do this, we have to take another step back to the very first lecture when we talked about the eye. So now you can see that all of this stuff, where I'm always, before I was always punting it off like, oh, we'll talk about this later, we'll talk about this later. It's starting to come together now, and it's a very exciting time for us here at E7. Okay, now the eye, we were talking about the rods and cones that exist within the eye. So if you remember, the eye is in the center of the eye, at least the color information is provided to us by the cone cells. And there's 3 different types of cone cells, but primarily we have the M and the L type cone cells in our eye. So we have the majority of the cone cells consist of the M and the L type, and the minority consists of the S type. And I believe that the average person, this doesn't mean that, I think when they say average, they just mean the average of all people, rather than, you take somebody randomly and that's an average person. The average person will have 98% M and L type and 2% of the S type. So this is a very big change in, excuse me, in the number of cone cells that we have. Okay, so I have an activity for you. So this is, again, we're going back to elementary school, and we have to do something like the teacher says, okay, class, now everybody do this. So I want you to close your eyes for a moment. Don't worry, I'm not going to do anything silly like start throwing stuff at you. And close your eyes for a moment and imagine that you have 3 rooms. They're all completely dark, and then there's a light switch. Okay, so you flip on this light switch, and each of the 3 rooms has a different color bulb. Room A has a red bulb in it, and it completely illuminates in red. Room B has a green bulb in it, so it's completely illuminated with a green light. Room C is a blue light. Now imagine that they're the same intensity, it's the same amount of light in both rooms, in all 3 rooms. Which room appears the brightest? When you go in, which room can you see the most in? Green, right, and that's exactly right. And that is because of the cone cells that we have in our eye. We are tuned, for whatever reason, most likely evolutionarily, that we are tuned to be able to see large gradations in the green color. And that is reflected in the fact that we have the vast majority of cone cells in our eyes are the M and the L type, which are stimulated mostly by green and to a lesser extent, but still to an extent, by red light. And blue light is all the way back here, detected by those S cones, just because it is a short wavelength. And in fact, that is exactly what appears to us in our eyes. So if you sort of imagine each of these is converted to grayscale, this should look kind of approximately right in terms of how bright this color is, how bright this color appears to us. The green is by far the brightest. Then there's the red, which is still kind of bright, but a little bit darker. And then there's the blue, which even though it is the same intensity as the red and the green, it is considerably darker to us. And if you're familiar, I don't know if all of you went through this, but when I was in elementary school, they had us do these hearing test. They put us into this room and they put a large headset on us, and they would gauge our response to various frequencies, like to determine, how tone deaf we were to various frequencies. And you could always tell which ones were just very, very hard to hear. They were so faint, even though they were probably at the same intensity. And it's the same sort of thing. Our ears have different response to different frequencies of sound, and our eyes have a different response to different frequencies of light. So this is very, very important to us when we're talking about luminance detection, or the brightness detection of a color, when we're trying to convert it to black and white. And we can actually quantify this into an equation. And in fact, that is what we do when we're talking about luminance. Yes, it's funny because there's more equations here, but this is important to us when we are calculating a luminance histogram. So a luminance value is made up by 30% red, about 60% green, and about 10% blue. So on a scale of 0, which is completely dark, and 100%, which is completely light, this is about how much each of these colors appears to us in brightness. So 60% is to green, so the majority of the brightness comes to us by green. Then half of that is red, and then poor old blue over there has the short end of the stick, so to speak. So we can then say that the green is twice as important as the red when we're taking color into account and converting it into black and white. And it's important that I'm talking about luminance. I'm talking about the apparent brightness of a scene and not any other type of black and white. So there's other ways that we could compute black and white from color, but I'm just talking about how we perceive the scene in terms of its brightness. Okay. And if we start bringing color into these histogram calculations, this should hopefully make a lot more sense. So when we see something that is only red, for example, it doesn't look very bright, not as bright as white, not as bright as green, but it's only sort of bright. And so if we have a photo that is only red, then we get this spike right here at about 30% of the way over in the histogram. Now, I should mention that whereas before we were talking about using just an average to try to calculate the histogram from the color information that we have, it still works out that we have an equation that looks sort of crazy like this. And the reason that this works is that these three numbers add up to 1. So what happens is that when we multiply, no matter what these numbers are within the range of 0 to 255, these numbers can be any number within that range. And when you add them all up, it will always be another number from 0 to 255. So you're not going to get more than that. You're not going to get less than that. It's always going to be somewhere right in the middle. And it works out. If we think of, if we have all red, so 255 red, all green, 255 green, and all blue, 255 blue, we expect that to be white, right? We were talking about mixing those colors, and we get white as the result. So if we did that, we get what for our luminance calculation? So you could actually do the math and figure out that, all right, I'll do the math. We could simplify the equation and make it a little bit easier, but we could also just do the math and make it a little bit easier. So let's say we said we have 0.3 times 255. So that's about 77. Okay, then I have, let's see, 255 times about 0.59 or about 0.6. That's 150.45. Okay, then I have the blue, 255 times 11%, 28.05. Now if I add those three together, you see that I get 255, which makes sense. So this equation still makes sense. Even if we have the complete presence of all these colors, which represents white, the luminance calculation still shows us that it is bright. It's fully bright as we would expect it to be. And similarly, it should hopefully be easy to figure out what 0 would be. It's just 0 plus 0 plus 0. So the luminance would then be 0. So here, when we talked about using the total presence of one color when we're trying to calculate one of these histograms, and we have red right here. Now remember that I said that if it's all red, it's 255 times 0.3. If you remember, it was about 77. And if you take a look at the data that exists here, you see that's precisely what this shows us. The average amount of data in this histogram is 76. The median is 76. The level is 76. That's because all of this information is right here at 76. And so this is proving my point where I said that we have complete absence of brightness here at value 0. Then we go all the way across to 255. That means that all these intermediate values are represented by the color. So at about 30% of the way, or a value of 76, we have this one large spike in the luminosity histogram. Okay, so what would this look like if it was all green? How would yeah, so it'd probably be like about right here, about 60% of the way over. And how about all blue? All the way right here, something like right there, about 10% of the way over. And again, if you don't believe me, you can actually open up a, you can go into Photoshop and just open any old object like this or any old document and then actually use, let's see, I said let's try blue. So I'm going to pick an all blue color down here using the color picker. Okay, click OK and then paint bucket it in. Now if I show you the histogram over here, hopefully I'm not going to embarrass myself. You'll see that it is exactly 10% of the way over. Okay, that's pretty cool. But one of the things that's really cool is if you were ultra nerdy, more so than me, and you actually try to make, okay, so imagine this. So you've seen how we can try to figure out a way that we can paint color into an image right here, and then actually show as a result some known spike in the histogram. So imagine you took that a step further and you tried to make an image in the histogram based on the values that you put here. And that is exactly what this one guy did, which is really awesome. He made this histogram right here, which is the old New York City skyline. And the image that made that is this gradient right here. And if you look at it, you'll actually be able to see that there's varying amounts of color. And actually, you'll also be able to see that there's, even though this is a grayscale, it's a grayscale gradient. In other words, it goes from black to white and the values in between. There's not supposed to be any color. You can also sort of see that there's like a kind of a green tint to it here. This is a good precursor to my big rant in a couple of lectures about properly calibrating the color of your monitor, because it will show you this color improperly. Okay, but getting sidetracked here. So now, if we look at this gradient, you'll see that there's varying amounts of each of these colors, and he was actually able to use that to his advantage to create a gradient like this. So it's pretty cool, and it's definitely a pretty good read. And if you really wanted to, you could copy this into Photoshop. It's very meta something. It's pretty neat. Okay. Anyways, back to this.